Hello and welcome to a new video in a course on linear algebra. In this video, we will be covering the concept of subspaces and we'll be going over some important examples of subspaces and some of their properties. Before we begin here, let me just say something here. So, there's always this debate whether one should be too light when discussing linear algebra or or like try to involve some tough things. So I'm trying to balance between these two. So in case you found me going too light, you can probably speed up the video to your liking. Or in case you found me going a little bit fast, you can just adjust the speed of the video. So I'll leave it to the audience to decide how the pace of the video should be, depending on how comfortable you are with the material. So let us start working on what's so-called subspaces. I'll be giving some examples of subspaces before actually defining what a subspace is. But let me just tell you in a few terms what a subspace is. Well, a subspace is a vector space that is contained in another vector space. And we call this vector space, we call it a subspace of the bigger vector space. That's it. This is the concept. However, saying this isn't a way of proving. Like if I give you a set and I tell you prove that this set is, or this set that is a subset of a vector space is in fact a subspace, like you can't just tell me like there's something to write down, right? There's something to prove. It's just not just words used here, right? So so let me just say the words that I said. A subset, let me just say it in this way. A subspace S of a vector space V is a vector space S that is contained in V. So I'm gonna put these between quotations because there's something here to add. It's not literally that. There's something that's still missing here. It's a little thing that just we need to take care of. So let me just start by giving you an example. So let's start with any vector space. So let us start with a vector space V, and I remind you this is a set which we equip with two operations, addition and scalar multiplication, and we require some axioms to be satisfied by this. Alright, so in every vector space there's what's so-called an additive identity, right? So we know in V, or maybe V is a bad letter here, let me just use omega, right? Because we're using V here. So in V, or in omega, excuse me, there is an additive identity which we usually call 0, right? So this vector, which we call 0, usually has the property that if you add 0 to any other vector V, you get V back. So this is the definition of 0, right? So this is for every V in omega. So this is the definition of the 0 vector. And now I'm telling you, if you take the set that contains only 0, and let's call it V, right? Let's take the set that contains only 0, right? This set is itself a vector space. But what operations are we talking about here? Well, we're talking about the operations that omega has, right? The operations, the addition and the scalar multiplication that omega has for itself, that are defined for omega. We're using these for this set, right? Because 0, remember, 0 is just an element of omega, right? So this addition and the scalar multiplication are defined for this vector, right? Are defined like it makes sense to say I'm adding 0 to 0 because this addition is defined for this 0, right? The 0 vector. And it makes sense to say I'm multiplying this vector by a real number because it's also defined for this vector what it means to multiply it by a number, right? So we're saying that this candidate is in fact a vector space. Well, this is clear enough. Like there's literally nothing much to say here, right? So this set, right? I remind you, like, there are three important things to check when we want to check a candidate is a vector space. Well, the first thing we need to check is closure under scalar multiplication and addition. Well, that is evident because, I mean, 0 plus 0 is 0, and this is still in V. This is still in the set V, right? And take any real number and you multiply it by the vector 0, you get 0 back, and that's it. I mean, 0 is still in V. This is closure. And the other thing that you need to check is the additive identity, which is 0 itself. So the additive identity is the identity. 0 is the identity. And it's also in V. And the third important thing that we need to check is the additive inverses. So does any vector in V have an inverse? Well, the only vector in V is 0. And what's the inverse of 0? Well, it is 0 itself. And why is that? Because 0 plus 0 by definition is itself 0, right? What's the definition of an inverse? The definition, if you have a vector V, the inverse of it is another vector omega, which when we add these, we get 0. We get the identity, right? So this is what we have. Alright, so 0 itself, which is the inverse of 0, is also in the set V, which makes V, because the other properties are easy to check. I'm gonna leave them for you to check because we haven't changed the operations. The other properties are easy to check. This makes V itself a vector space. But hold on, V is 0, and 0, this as a set is a subset of omega, right? So this vector space as a set, it's a subset of the set omega, right? But this is a vector space and this is a vector space. So these are vector spaces. Thus we call V a vector space, a subspace of omega. I mean, this is as clear as it sounds. There's nothing hard about it, right? So we're gonna take more complicated examples, but I hope that the idea is clear. Here's a cleaner proof of the properties of why the trivial vector space. By the way, we call this vector space. If you take just the set 0, we call it the trivial vector space, okay? So here's a check of why this is a vector space in a clearer, cleaner proof. All right, so let us take another example. Let's take another example before actually giving the formal definition of what a subspace is. So consider the set. Consider the set of all numbers in R2. I remind you, R2 is the Euclidean space, which we proved a few videos ago. We proved that R2 is itself a vector space, and it's the set of all tuples where we define addition in this way and we define scalar multiplication in this way, right? So we define, these are what's so-called element-wise operations. So what we're saying is that we want to take V to be the set of all elements in R2, all tuples in R2. Like this is the set of all tuples x, y, where x is in R and y is in R. X and y are real numbers, okay? We're gonna take the set of all tuples, and what we're gonna do is that we're gonna require that their sum is 0, right? So for example, the element 2, -2 is in V, because 2 plus -2, first of all, because 2 and -2 are real numbers, and second, because their sum is 0. This makes 2, -2 in V, right? This makes this element in V, right? So we're taking all of these elements, we're collecting them together, and we're calling this set V. And I'm gonna claim now, so my claim is that V is a subspace. I'm gonna put this between quotation because I haven't defined what a subspace is yet. Well, I did, but I haven't written things in a clear way. So V is a subspace of R2. So let us see why this is the case. Well, this is also evident, but let's see why. So so I remind you there are three things that we need to check, and the rest usually follow by easy check. So the first thing that we need to check, first of all, what are the operations that we're using for V? And these operations, are they binary? In other words, what is the addition and scalar multiplication that we're using for V? And is V closed under these operations? Well, so what we're gonna do is that V, we're gonna take the plus and the dot. And these plus and dot, these are the operations defined for R2. So we're gonna take these as like these are gonna be the inherited operations. Like we're gonna borrow these from R2 and we're gonna give them to this subset of it, right? So this is another important thing that I'm gonna stress when I define a subspace. Like the subspace and the vector space should have the same defined operations, right? The plus and the dot, the scalar multiplication should be the same. Okay, so what we're gonna do here is that we're gonna take these two operations and we're gonna define these, we're gonna equip V with these, all right? So now that we've done that, we have a legit question of whether or not V is a subspace. And what does it take for us to check that V is a subspace? Well, we have to check that V is itself a vector space. And I'm not gonna hold this anymore. Let me just tell you what's the additional thing that we're requiring. So we're gonna just state the definition below for what a subspace is, but I feel sorry not telling you this. So a subspace S of a vector space V is a non-empty, this is the first thing that I didn't mention above, is a non-empty vector space that has the same operations as V. This is the second thing I didn't tell you about. It should have the same operations, like the same addition and scalar multiplication as those of V, that is contained in V, right? So S is contained in V. S is itself a vector space. S has the same operations. And S is not empty. So this is the empty set. It's not equal to the empty set. Alright, so this is as clear as it sounds. So it's a subset. It's a vector space when we equip it with the same operations of V, and it's itself non-empty. So I remind you here, since we talked about this trivial subspace, it's clear that V here is not empty because 0 is there, right? This is not the empty set. And it's also clear that what we did here is that we equipped this set V with the same operations as the vector space omega that we were talking about. Okay. So these are this is what it takes for a subset of a vector space to be a subspace. Okay. So let us go back here and check that this is really a subspace. Well, let us check that. Well, first of all, this V, I'm gonna remind you here, this V is defined as such, and it's a subset of R2, and we're gonna equip it with the operations of R2, and thus our question becomes legit of whether or not this is a subspace of R2. And there's one more thing that we need to check, because as I told you, we need an additional thing before we check that V is a vector space and hence prove that it's a subspace. We need to prove that V is not empty. Well, V is not empty because 2, -2, for example, is in V. So V is not empty, right? So since V is not empty, now our question is legit, and we're gonna prove, this is the proof of V. Well, this is the proof, let's say. Proof starts here. Okay. So the first thing that we checked is that there are, like, V is equipped with the same operations of R2. And the second was that V is not empty because it has an element. And then we're going to prove that V is a vector space, right? So the second thing we need to prove is that V is itself a vector space. And this is what it takes for V to be a subspace. But what does it take for V itself to be a vector space? Well, we said that there are three important things to check, right? So the first thing that is needed to be checked is that V is closed under addition and scalar multiplication. So the first thing we need to check is closure. And perhaps I should show you the cleaner proof because we're running out of space. So let us come here. Come. So let us write things here. So again, I'm gonna write you V here. So V is the set of all xy in R2 such that x plus y is equal to 0. So this is the set that we're talking about, and we're claiming that this is a subspace of R2. We were left to prove, like, what was left to prove is that V is itself a vector space. So let us prove that V is a vector space. Well, the first thing, like, there are a few things to check that are important. The closure under addition, closure under scalar multiplication, closure under, the existence of identity, and the existence of additive inverses. And once we check these, the rest of the axioms of vector spaces will follow easily because we're using the same operations of V, okay? Of R2, excuse me. So why do we have closure under addition? Well, closure under addition happens because, so if you look at, if you take any two elements, x, y, and let's say a, b, how are we going to add these? Well, the way we're going to add these is that we're going to add the first to the first, so x plus a, and then y plus b. So this is because we're using the same plus of R2, right? So we're gonna start, let me just write things here. Start with xy and ab in V, okay? And we want to prove that their sum is also in V. Now, since xy and ab are in V, now let us do this one at a time. Since xy is in V, then x plus y is 0, because this is what it means to be in V, right? And since AB is in V, we're gonna have A plus B is also equal to 0. So this is also by the way we defined what V is, okay? Now we want to check that this element is in V. Now this is a tuple in R2, right? So this is the first part of what it takes for an element to be in V. And the second part is that it should be that the first component plus the second component is 0. But the first component plus the second component is this. But we do know that this thing plus this thing is 0. So the sum of these is 0. And we know that this thing plus this thing is also 0. And thus we have 0 plus 0, and thus the whole thing is 0, which makes this whole element in V. So this proves that we have closure under addition, as clear as it seems. Now, closure under multiplication, well, so let xy be in V and R be a real number in R. So we're gonna prove this. How are we gonna prove this? Well, we're gonna prove that R dot xy is also in V, right? So, but remember, since we're borrowing the scalar multiplication of R2, this is just the element wise. So this is Rx, Ry. And now we want to prove that this is an element of V. But why is this an element of V? Well, what does it take to be an element of V? Well, it takes that it should be a tuple in R2, and it should be that the first component plus the second is 0. Well, it is a tuple in R2, right? It's clearly a tuple in R2. And why is the sum of the first and the second is 0? Well, we do know, since this is so, since xy is in V, then x plus y is equal to 0. So this is something that we know, right? And thus we wanna see if whether or not Rx plus Ry is 0, but Rx plus Ry is R into x y, right? And then x plus y, excuse me. And then this is what? This is R times 0, and this is 0, which makes this whole thing in V. So we just proved that we have like closure under addition and scalar multiplication. So the next thing that we need to do is additive identity. So why is there an additive identity in V? Well, here's a trick for you. The additive identity of the subspace has to be the additive identity of the vector space that we're talking about, right? Because remember, the additive identity is this vector 0, which when added to any other vector, it gives 0. It gives the vector back, right? So what's the we're gonna come back to this as a property of subspaces, but let's see here. So R2 has the 0 has the additive identity 0 0. Remember this. When we proved that R2 is a vector space, we proved that this is the additive identity of R2, which means if we add 0 0 to any other vector, we get that vector back, right? This is the definition of additive identity. Now we want to check whether this additive identity is in V. Well, what does it take for it to be in V? First, it has to be in R2, and second, we should, like, their component should add to 0. But their component in this case are 0 and 0. But 0 plus 0 is 0. Thus 0 0 is in V. But since it's in V and it has the property that if you add this to any other vector in R2, and specifically to any other vector in V in this case, because V is a subset of R2, then 0 is itself an additive identity of V, because 0 0 plus xy is equal to xy for every xy in R2. This we know because 0 0 is an additive identity, but R2 contains V, right? So this proves that 0 0 is an additive identity of V. So so this is what we have, right? So the last thing that we need to check is the additive inverses, right? We're gonna start with any vector in V, all right? And what we're gonna do is that we're gonna, just as we did for R2, because when we spoke of the inverses in R2, what we did is that we took this, we took the negative the first component and negative the second component as the vector to be the inverse, right? And we check that when we add these two, we get 0 0, and this is clear because this is the inverse of the vector in R2. Now the question here is this inverse in V? Well, sure it is, because since we're starting in an element in V, this implies that x plus y is itself equal to 0, because this is the defining characteristic of what it takes for you to be in V. And we check now that this element is in V. Well, negative x plus negative y, because remember we need to check that the first component plus the second component is equal to 0. This is equal to negative x plus y but this is equal to -0 because this is what we have, and thus this is equal to 0. And thus this proves that this element is in V. So so inverses exist in V as claimed. And thus, after you check the other properties, which will follow easily, I'll leave them for you to check, the other axioms, you will see that V is a vector space. So since V is a vector space, so this, let me just mention here, this is checked below. Okay. So since V is first of all non-empty, and it's contained in R2, it inherits the same operations as R2, and it's itself a vector space, just as we checked before. Thus we call V a subspace of R2, right? Now, okay, so this completes this example, okay? Now you might ask yourself, well, isn't it too much to check that something is a vector space? Like, we're checking a lot of things, right? It would be easier if we had kind of like smaller number of properties to check rather than having to check all of these stuff. Well, yes, there is, and you'll be surprised that like the way we're gonna define subspaces now is a little bit like surprising for you, but I'm gonna convince you that the way I defined it at first and this way are one and the same. Like you can define a vector space in either a subspace in either way. You can define it as a non-empty vector space that has the same operations as the bigger vector space, and it's contained in that vector space. So this is one way to do it, just as we talked about before. And there's another easier way of seeing it, especially when it comes to checking if a subset of a vector space is a vector space, is a subspace. And this is the way, okay? So this is the way we are gonna define it. So let me just give this another definition, and then we're gonna summarize things again, okay? So let V be a vector space, okay? We're starting with any vector space. It of course has addition and scalar multiplication defined for it, okay? A subspace omega, okay? A subspace omega of V is a non-empty. This is one thing I need to like, I can't stress enough. It's a non-empty subset of V. So it's a subset of V, it's not empty, and it's closed under addition and closed under scalar multiplication. And that's it. This is all you need to check. Like, if I give you a vector space and I tell you, look at this subset of that vector space and equip it with the two operations that the vector space has, tell me whether or not this subset is a vector space or is a subspace. Well, the only thing that you need to do is check that it's not empty, and by that I mean find an element there, right? Find an element there so that you can convince me it's not empty. And the second, like the second thing, prove it's closed under scalar multiplication, and the third thing, prove that it's closed under closed under addition and then closed under scalar multiplication. And that's it, right? So so let me just before I state this proposition and prove it for you, let me just tell you here, so here's a big note, I would say. If I ask you to prove that V, let's say with plus and times, is a vector space or a subspace, and I want to stress here on vector space, because remember, to prove a vector space we had to check around 10 axioms, right? Or more actually. So now if I give you a set with two operations and I ask you whether or not this is a vector space or whether or not this is a subspace of another vector space, you only need to check that it's non-empty. This is property, let me call it property 0. Property 1, it's closed under addition, and property 2, it's closed under scalar multiplication. If you could find a relevant vector space, like if like let me just restate what I said. If I ask you to prove that V is a vector space or a subspace of omega plus dot, you just check 0, 1, 2, the properties 0, 1, and 2. But let me be clear here. It's clear that when I ask you to prove that something is a subspace of omega, that 0, 1, 2 are enough to check, because this is how we're defining what a subspace is, okay? But what's not clear so far, because I mentioned this, is that why if I give you any vector space, it's enough to check that it's enough to check these three properties. Well, I'm not saying that it is enough for any vector space. I'm saying if you can find, if this vector space, like, you know, it's a subspace of a bigger of a bigger vector space, like say you have a vector space V, right? And I give you an example, let me call it a vector space omega, right? And I give you some complicated definition of V, but you do know that V is a subset of omega. And I ask you, prove V is a vector space without anything else. If from your knowledge you know that, if you know that V is a subset of omega, it's enough to prove that V is a subspace of omega. If we're using the same operations, of course, is a subspace of omega, which means it's enough, i.e. enough to show 0, property 0, property 1, and property 2. Property 0, property 1, and property 2. Okay? So this is a big tool for you when you're faced with the problem of prove something is or is not a vector space, right? In that case, if you know that this is contained in a bigger subspace, for example, most of the time you will see complicated examples of, like, you take a vector space that is subset of R cubed and you impose some condition here, like you impose some conditions on the elements of R3, like for example you impose that x, y, z, because the elements of R3 are in the form x, y, z. For example, you impose that their sum is 0, right? So this is something that you impose sometimes, and you face the question that prove that this is a vector space. Well, instead of you having to check all the axioms, all the 10 axioms, now you only need to prove that this is a subspace of R cubed, which means it's enough to prove 0, 1, and 2, and that's it. Now, if you do that, you get that this is a vector space. Okay, so this is an important trick to keep in mind, because you will use it. I guess you will use it a lot. All right, and now that I mentioned this trick, I should tell you, I should convince you why this is the case, why it is true that these two definitions that I've given you of vector of subspaces are the same. So this is the task of this proposition 4.1. A non-empty subset omega of V, right, is a subspace of V. So we have V is a vector space with two operations, and we're saying if you start with a non-empty subset omega of V, right, then this omega is a subspace if and only if omega is itself a vector space, right? So let me just restate what I said here. So we defined previously a subspace as a vector space that is contained in a bigger vector space, right? So this was our definition 1. So this was our definition 1. And in definition 2, we define the vector space as we define the subspace as a subset that is non-empty and that is closed under addition and scalar multiplication. So we're saying these two definitions are the same, right? So let me just write you definition 1 here because it's important to keep it in mind. So definition 1, a subspace omega of a vector space V is a non-empty subset of V which, when equipped with the same operations forms a vector space. In other words, the first definition is saying to check that omega is a subspace of V, you will need to check that omega, let's say V is defined with these operations, plus and times, scalar multiplication. You will need to check that omega is not empty, omega is a subset of V, omega has the same operations as V, and omega is itself a vector space, right? So this is the definition 1. Definition 2, we're saying that the other way to define what a subspace is that it should be a non-empty subset. It should be a non-empty subset of V that's closed under addition and scalar multiplication. So this is all we're requiring. But it seems that in definition 1, we're requiring more stuff than in definition 2. Because, you know, if we're requiring omega to be a vector space, we are like immediately requiring it to be closed under addition and scalar multiplication. Like, it seems that we're kind of dropping a lot of axioms and we're assuming that they should hold, right? They should hold in some way. And this is what proposition 1 is saying. Proposition 1 is saying, proposition 4.1 is saying definition 1 is equivalent to definition 2. So this is an if and only if notation, right? Definition 1 is equivalent to definition 2. So let us prove this. So let us prove why this is the case, why it's true that these two definitions are one and the same. So let us prove this direction, okay? Let's start by proving this direction. So if we assume definition 1, so assume definition 1, then what do we have? Well, what we have is the following. We have omega is non-empty from here. From where? From here. Omega is non-empty. Second, we have that omega is a subset of V from here. Third, we have omega has the same operations. So omega has the same operations. And 4, we have that omega is a vector space. Okay, so let's see if this implies definition 1. Well, first of all, it implies that it's a subset. It's a subset of V. Second of all, it implies property 0. So let me just say property 0 here, done, right? And this is done, right? And we require that it's closed under the addition and scalar multiplication. But since omega is a vector space, then it's automatically, then omega is closed under addition and scalar, because this is the definition of a vector space, right? This is some of the axioms of the vector space is that it's closed under addition and scalar multiplication, right? So I guess this completes the proof, because definition 1 entirely implies definition 2. This is as clear as it seems, right? So this completes the proof of the first direction. And this is a notation for the end of the proof. Like, you write a box and you fill it out. So let us prove the other direction. Let us prove that definition 2 implies definition 1. So now what we're gonna prove is that if we assume that a subset omega satisfies these properties, then it should satisfy these properties. So let us see why this is the case. So bear with me because this is a little bit tricky here. There are a few tricks here to do. Okay. So we're assuming definition 2. So assume definition 2. Right? And we want to prove definition 1. We want to prove that the properties in definition 1 are satisfied. Well, if we assume definition 2, then first we have omega is a subset, and we have omega is non-empty, and we have closure under addition and scalar multiplication. So we have omega non-empty, omega is a subset of V, omega closed under plus and times. And let us check that definition 1 is satisfied. Where is definition 1? Here it is. Here it is, okay? So I guess I should start using colors here because it's important. So what are the things that we need to check? This is the first thing. This is the first thing. Non-empty. It should be a subset. But, well, non-empty is clear from here, right? It's a subset is clear from here, right? And so we want the same operations. We want the same operations. Well, we're talking about the same operations, and we're saying that omega is closed. Now the hard thing, or the thing that requires some work, is that why it is a vector space, right? I'm only giving you that it's closed under addition and scalar multiplication. Like, there are properties that we haven't checked, for example, or we haven't required, for example, existence of zero, existence of inverses, the distributivity, commutativity, the other axioms of vector spaces. So how is it true that these alone, like the closure under addition and scalar multiplication, are enough to prove that omega is a vector space? Well, let's see why. So again, I'll prove to you. So we want to prove omega is a vector space. Okay? Now omega is equipped with the same operations. Okay? So this is what we're talking about. Well, first off, omega is closed under addition and scalar multiplication. So I remind you, these are one of the important properties of proving a vector space, right? Of proving a set is a vector space. So it's, first of all, this we have from here. So the next thing is, why does the zero exist? Why is there a zero? So this will come from here. Let me show you why. Okay, so let me show you why. Omega is not empty. So this, we have this, right? Since omega is not empty, then there is some v in omega. So there is some vector v in omega because it's not empty, right? But since there exists some v in omega, then let us consider 0 times v, where by 0 I mean the real number 0. Because remember, scalar multiplication is defined between scalars and vectors, and this is a vector, right? So 0 times v is 0, right? But here is an important thing. First of all, this is the vector 0. This is the vector 0, and which vector, which vector space is it coming from? Well, it's the vector space v, because remember, v is a vector space, and when we multiply 0.v, we proved in the previous lecture on the properties of vector spaces that 0.v is itself equal to the 0 vector. But here comes another important property, which is the closure under scalar multiplication. So, which means if you take a vector in omega and you multiply it by any real number, you get also a vector in omega, which means that this thing, since v is in omega, this thing is in omega. And let me just state here why. Because omega is closed under the dot, right? Which means that 0 is in omega. So this proves existence of additive identity. And why is 0 an additive identity of omega? Well, because 0 plus v is equal to v for every, let me just use omega here, for every omega in the bigger set v. So remember, 0 is the additive identity of the vector space v, right? Then if we add 0 to any other vector of v, to any other omega, we get 0. But particularly, if we add 0 to any other vector in omega, because omega is contained in v, then any other vector in omega will satisfy this property. And thus 0 is an additive identity of omega. But we already showed that 0 is in omega, right? So this is the second thing that we need to check. The third thing that we need to check is the existence of additive inverses, right? So let v be in omega, and we want to find an inverse. We want to find an inverse to this vector in omega, right? So I remind you, we should find an inverse, and it should be in omega. This is very important, right? So, well, you do the obvious, because, so here's v, right? What you do is that you add -1 times v, right? This is very important, right? Please. All right, so far what we did, we started with v, and I'm claiming that this is the inverse. But before I tell you why this is the inverse, let me just remind you that omega, what is it? Omega is closed under scalar multiplication, right? Omega is closed under scalar multiplication, which means since this is a number and this is a vector in omega, and this is scalar multiplication, then this whole thing is in omega, right? So the inverse, if I tell you why this is the inverse, then the inverse is in omega, and this is what we want to prove, right? But I remind you from the previous video on the properties of vector spaces, we proved, like you can check that video in the description below, we proved that -1 times v is itself -v, is itself the inverse of v. This is something that we proved in the previous video. You can check it out. And this is equal to 0. This is the 0 of v, but the 0 of v is itself the 0 of omega, and thus minus, like, this thing which is in v is in fact the inverse. So this thing is the inverse, and it is in omega, and thus proves existence of additive inverses. So far so good. Let me just show you what we did. We started with the assumption, the only assumption, that omega is not empty. Like, we mainly started with definition 2, but this is the same as omega not empty and omega closed under addition and scalar multiplication. And then we said, well, we want to prove that omega is a vector space, because this is what is left for it to satisfy definition 1. And then we said, well, it's closed under addition and scalar multiplication, so we're trying to prove that it's a vector space. it's closed under addition and scalar multiplication, it has the 0 and it has inverses, and thus the other properties will follow easily because we're using the same addition and scalar multiplication, so the other properties of vector spaces will follow easily. I'm gonna leave them to you as an exercise. And then that's it. This proves that omega is a vector space, and this proves that omega, if it satisfies definition 2, if it satisfies this, then it should satisfy this, right? So these two definitions are one and the same. You can use any of these to prove that a subset of a vector space is or is not a subspace, right? And yeah, this was a long discussion, but it's definitely worth it. These are two important definitions of what a subspace is, and you can use any of these, but of course you should smartly use the easier one, the easier criterion, right? But the reason we proved this equivalence is to tell you that if you want to prove something is a vector space, it's enough to find a bigger vector space, just as I described you before. It's enough to find a bigger vector space that you already proved before, and it's enough in that case to prove that it's a subspace. Like if you want to prove something is a vector space, it's enough to prove it's a subspace, which means it's enough to check 0, 1, and 3, right? So this is all I wanted to say about this. And I'm gonna leave for you here a cleaner discussion to look at this, right? It's important. So look at this in your, you can pause and look at this. So we will have to do one more lecture on this chapter before we transition to linear transformations. So yeah, it's important to go over these. These are worth it, definitely. So thank you for listening.